Good evening, students. My name is Shashank Shekhar, and we are doing a crash course on chemistry of 45 days for the upcoming JEE exam. And today is our 18th day. So, today we will be starting the new chapter, that is electrochemistry. So, we will discuss this chapter in two parts. The first will be contained of the conduction and everything. The second will be contained about this electrochemical cells and fuel cells. So, let us start our class. The current which we will talk about in this chemistry will be mainly consisting of this electrolytic conduction. Whether it will not be about the metallic conduction, which is mostly covered in the physics. So let us see what is the difference between this electrolytic conduction and the metallic conduction. The first and the foremost difference is that the flow of electric current is due to the movement of ions. Okay, so it is due to the movement of ions. So you know very well that whenever an electrolyte is dissolved in water, it gets its aqueous form and releases ion. And depending on the nature of the electrolyte, whether it is strong or weak, it will release the number of ions. So you have studied this thing in the chapter, that is ion equilibrium as well. Now, the second point is that the electrolyte must be in the molten state or the aqueous state. So, the meaning is that you cannot conduct electricity if the electrolyte is in the solid state. Likewise, if you have NaCl, that is sodium chloride salt, and if you just use the sodium chloride powder form to conduct electricity, it will not be even possible. So for that you have to dissolve that sodium chloride into water, that is the aqueous form, or you can get the molten state also for some electrolytes. Now, electrolytic conduction also follows the Ohm's law only, that is V is equals to IR, R is equals to rho L by A. All those formulas that we have for metallic conduction is applicable for this electrolytic conduction also. The most common examples are the acids, bases, and salts. So all acids and bases and salts are electrolytes, and they do electrolytic conduction. Now, depending upon the nature of the electrolyte, whether it is strong or weak, the amount of current that will be passed will depend. So for you will know very well that strong electrolyte do dissociate completely, while weak electrolyte like weak acids and weak bases, they dissociate in up to a certain extent. So they conduct less amount of electricity. So keep these things in mind. We will use those concepts of ion equilibria in this chapter also. Now the next, which we will not study much about, is the metallic conductance. So in metallic conductor, the most of the current is due to the movement of the free electron that is present in the metal. Now, which type of metal do conduct electricity? Which have the free electron. So in the free electron, we mean that the gap between the conduction band and the valence band is less. So in a brief, you can say that. So when we will study solid state, we will see this property more closely. But what is the meaning of this free electrons? And the most common example of metallic conductor, copper, iron, and gold. Yeah, so there are many metal which can conduct electricity like copper, iron, gold, or you can say silver also. So these are the main properties of these metallic conductors. Now let us see some of the terminologies which we will be using throughout this chapter. Like we have already an idea about what is resistance and what is resistivity from our physics knowledge, that it is R is equals to rho L by A and rho is equals to R A by L. Now we have some another other terminologies like the conductance and the conductivity, which are more important in this electrolytic conduction. So we will see them one by one. The first one is conductance, and it is represented by the symbol G. Now, what is conductance? So, it is the measure of the with which an electricity can pass through a substance. So, let us first of all see conductance, then we will see conductivity, and we will see what is the main difference between both of this. So, it is the measure of the ease with which an electric current can flow through the substance. So, keep this definition in mind. So, you can see it has a measurement. It is not can say that okay, so this is the length and this is breadth. This is not this kind of property. So it is the measure of the ease, just like permeability we have. So a substance is permeable means the amount of current that can be passed through it. Same thing, it is the ease with which a electric current can flow through a substance. Uh, Going to the definition part, it is not important for the numericals. Most of the questions are asked from this formula, so you must concentrate on formula more. Now, the next and the most important property is that conductance is an extensive property, which means that if you change the concentration, it will change the conductance. Okay, so conductance depends upon the you can say the number of ions and all. So because it is an extensive property. Now the next is that its unit is mho or rho. This is omega inverse, or you can say Simon. So three units are there, so all have the same equivalence. So one mho is equals to one rho inverse, or is equals to one Simons. So what is the formula for this conductance? So it is given by G is equals to 1 by resistance. So by resistance we mean that what is the it is a measure of how a conductor can resist the flow of electricity. Now since G is just opposite of that, or you can say reciprocal of resistance, so it is the measure of ease with which electric current can flow through a substance. Now we know that 1 by R, so what is the unit of R? It is omega. So 1 by omega, that is omega inverse. We also use this also, that is Siemens. Now the next thing is the conductivity. So what is conductivity? It is the property of the material by virtue of which the material offers ease in the flow of current. So the conductance is the measure with which measure of the ease with which electric current can pass through it. So in this case, conductance, we are measuring the ease of the material, of ease of the current. But in the conductivity part, we are measuring the property of material. So this is the main difference between both of this. So it is an intrinsic property of the material, conductivity, where conductance is not so. So it is an intrinsic property overall. So it depends upon the nature of the electrolyte that we are using. And what is the unit for it? So it is just the opposite of resistivity. We know very well that resistivity this is symbolized by this term rho. So opposite of rho is called as the conductivity, and it is denoted by the symbol kappa, where kappa is equals to 1 by rho is equals to L in by A into conductance. Why? Because we know that R is equals to rho L by A. So if we calculate 1 by rho, it would be 1 by R A by L. Okay. Now 1 by R is nothing but conductance. Okay. In this way, it is that. Okay. So 1 by rho will be L by A. Sorry. L by A. Yeah. So this will be the formula. In this way you can derive this formula, which will be conductance into L by A. So the same thing is written here. So it is L by A into conductance. Now let us move to another property of the electrolyte, that is molar conductivity. So by conductivity we are not defining the amount of concentration that we are using. Now if you say that it is molar conductivity, then it is the amount of means it is the can say we are fixing the or specifying the amount to 1 mole, that is we are taking 1 mole of the electrolyte. So it can be defined as it is the conductivity of a solution containing 1 gram mole of electrolyte dissolved in a certain volume of the solution. Now here one thing is to mention is that the volume of the solvent is not fixed, only the concentration of the electrolyte is fixed here. Sorry, the number of the moles of electrolyte is fixed here. So you can dissolve this 1 gram mole of electrolyte into 1 liter or 2 liter or 3 liter. It does not depend on that. So molar conductivity is basically putting a barrier on the number of moles that you are dissolving in a given amount of solution. Now if you go to the unit of specific conductance, so it is Simon centimeter square per mole, or you can also have per ohm centimeter square per mole. So if you want to derive this, you can do it so by looking at this formula. So what is this formula? It is the formula for molar conductivity. It is given as kappa into 1000 by molarity. Okay. So it is given as kappa is equals to lambda m is equals to kappa into 1000 by molarity. So why are we multiplying it by 1000? To convert this decimeter into centimeter. So we are converting this decimeter centimeter. So we are multiplying into 1000, because we see here that it is having a unit of centimeter square, not decimeter. So we are first converting this molarity in terms of centimeter. So we know that 1 centimeter is equals to 10 decimeter, or you can say that 1 decimeter is equals to 10 to the power 1 centimeter. So we have a volume. So volume is 3 times L, or you can say 3 times length. So it will be 1 decimeter cube, which will be 10 to the power minus 3 centimeter. So this same 1000 is factorized here. So it is kappa into 1000 by molarity. So you can see here very clearly that conductivity is nothing but it is for 1 m of the conductivity of 1 m of the substance, or you can say 1 gram mole of that substance. It is kappa into 1000 molarity. So if you want to take out the unit of it, so we know that for kappa it is Simon per centimeter. Now molarity will be per mole, and for molarity it will be per mole into centimeter cube. That will give us Simon centimeter square per mole. So this same thing is written here, Simon centimeter square per mole, or you can also write per ohm for this, which will be this. Okay. So this is the SI, this is the unit of molar conductivity. If you want to clarify these terminologies more and more, you must solve numericals as much as possible, so that you can grasp, get a, you can say a quick grasp on these formulas, because mainly the formulas are important throughout this chapter, means throughout this unit you can say. So because I have divided this into two parts. In the second part we will study about the Nernst equation most of all, and its uses. But in the first we will see this conductance and conductivity and all of this property, which I have mainly many formulas through it. Now similar to this molar conductivity, which we will have this equivalent conductivity. So the only difference is that we are considering 1 gram molar. Here we are considering 1 gram equivalent of the electrolyte, and not defining this volume again. So we are taking a an anonymous volume, and we are dissolving 1 gram equivalent of electrolyte in that solution, and then we are calculating this lambda. That will be called as lambda equivalent. Sorry for this mistake. It will be lambda EQ is equals to kappa into 1000 by normality. So for gram equivalent we will have molarity, and for this we will have normality, and we know the relation between it. It is n factor into molarity. So n factor is different for different compounds. So different electrolyte it is different. Okay, so this is the thing here. Now next is the Debye-Huckel-Onsager equation. Now this now we will see the variation of this properties like molar conductivity with the concentration, and for that the first law that was given by Debye-Huckel-Onsager, and it is for the strong electrolyte. So keep this in mind always, that this Debye-Huckel-Onsager equation is always used for this strong electrolytes. So it is given as lambda is equals to, so lambda m is equals to lambda naught m minus AC half. Now the important thing to note here is that the first new thing is here, it is called as limiting molar conductivity. So you can call it as the infinite molar conductivity also. So it is the molar conductivity that is at the infinite dilution. So we are taking a say a solution, and we are dissolving 1 molar gram of that electrolyte, and now we are increasing the decreasing the concentration, increasing the concentration, that it is having an infinite dilution. So at infinite dilution, say we are dissolving 1 liter, then we are dissolving 2 liter, then we are measuring the lambda m, and it goes on increasing, and at that point where this lambda m reaches its maximum, and upon further dilution we do not see any change in this lambda m, then we call it as lambda naught m. Okay, So it is a limiting molar conductivity. So the relation between these three is given as lambda m is equals to lambda naught m minus AC half. Now here the A is called as the Debye-Huckel constant, and it depends upon the electrolyte that we are using. So it is a specific property of the electrolyte, and while you are solving the question, this value will be given this value will be given always. Then C to the power half, that is concentration half, and this concentration will be molarity. So mainly molarity is used here as concentration. So this is the thing we have. Now if we take this equation, lambda is equals to lambda naught m is minus AC half. So this is the Debye-Huckel equation we have. Now if we compare it with the equation of a straight line, which is as y is equals to mx plus c. So on comparing we get that, so since we are drawing a graph between lambda m and root c, and we can also see here that this thing is constant. Okay, so this is constant because it is upon you can say uh, infinite dilution, so it is constant, so it is the c here. And what is lambda? Y is lambda here. So let me write it like this. So y is the lambda, c is lambda naught m. Also this a is a constant, so it will be m is equals to minus a. So this will be the slope of the graph, and x is equals to root c. Now you can see very clearly here that whatever the graph we will get, it will have an intercept of lambda naught m and a slope of minus half, that it will have a negative slope. You can see the graph also here, so it is having a negative slope, and this intercept will be equals to lambda naught m, and we are plotting lambda m against this concentration, that is root c. We are taking not c but root c. For strong electrolyte we get this kind of graph. Okay, so this is clear for all of you. Okay, now next we will move to the most important. So it is also important, but this Kohlraasch law has many applications, so it is asked multiple times in the exam also. So the next thing we will see is the Kohlraasch law. So any question you can ask from in this. Now the next is the Kohlraasch law. So what does Kohlraasch law say? That that the molar conductivity at infinite dilution is the sum of the individual contribution of its positive and negative ions. So say we have an electrolyte here that is having nu plus number of cations and nu minus number of anions. Then if you want to calculate the molar conductivity of the electrolyte, then how we will calculate? We will calculate it as lambda naught m is equals to lambda nu plus lambda naught plus and nu minus lambda naught minus. So let me write it here. So say we have an electrolyte and we have to find the molar conductivity at infinite dilution. Then what we will do is simply multiply the coefficient, that is the number of, say we have this electrolyte as A, which is present in nu plus amount, and B, which is present in nu minus amount. Now nu plus into lambda naught plus nu minus into lambda naught minus. So this is the limiting molar conductivity of this cation, and this is the limiting molar conductivity of this anion, and these are the number of atoms that are present of each cation and anion. So this is the formula that you will get. So this is the thing here. Okay, so you will use this limiting this Kohlraasch law for the very to and fro to solve many of the numericals. Now let us move to the weak electrolytes. Now if you see the graph of the weak electrolyte, that is for molar conductivity versus this root concentration, you will see a different kind of pattern, that is following a curve. Okay, so this is following a curve, not a straight line. So that's why the Debye-Huckel equation is not applicable for this weak electrolytes. Okay, so for weak electrolytes the curve that is obtained is different. Now for a weak electrolyte we have a different kind of relation. So it is related mainly to ionic equilibrium. So that's why I have said that ionic equilibrium chapter may be used in this chapter as well. So if you want to calculate the fraction of molecules that have dissociated, or you can say degree of association or dissociation or ionization, it is calculated as alpha is equals to lambda m at by lambda naught m, where lambda m is the you can say conductivity at a given concentration divided by the molar conductivity at infinite dilution. So say you have to calculate alpha at a given concentration, then you will simply calculate the molar conductivity at that concentration divided by the molar conductivity at infinite dilution, and this ratio will give you the alpha here. Now for weak electrolyte, we know very well that dissociation constant is given as C alpha square by 1 minus alpha, so it is given in this way. So we have not neglected this alpha here, although it is much more smaller than 1, we have kept it. Now we are substituting it one by one. So we know that this alpha is equals to lambda m by lambda naught m. So same thing we have put here. So let me do it for here, do it you for here. So we know that k is equals to C alpha square by 1 minus alpha. So if you put the value of alpha here, so it is lambda m by lambda naught m whole square by 1 by lambda m by lambda naught m. So in this way we can get this equation. Now if you divide this whole by lambda naught m, it will be like this. Okay, so this is the final equation we have. Now this equation will be used further. Okay, so this was the case of variation of molar conductivity with change in concentration for strong and weak electrolytes. So we saw two cases. The first one is that we got a straight line for the strong electrolyte, which was like this. So this is the for strong electrolyte. Which follows the Debye-Huckel-Onsager equation. And for this, we got a curve like this, which is for a weak electrolyte. And the formula that can be used to quantify it is alpha is equals to lambda m by lambda naught m, where alpha is the degree of dissociation. Now further, we have used this alpha to find the dissociation constant. So it is an equilibrium constant also. Then the thing that comes to our mind is how do we measure the resistance and resistivity and conductivity and all of this for electrolytic conduction. So for metallic conductors, this thing is quite easy with the help of this Wheatstone bridge. So you must have studied this Wheatstone bridge. So we do conduct a bridge like this. Suppose it was like this something. Okay. So we do have a bridge here, and we use this bridge in some way to calculate this resistance of this. Say we have to calculate some resistance of this metallic, and we put it there, and we balance R1 by R2 is equals to something like that, and we do it. Now for a electrolytic conductor, the first problem that comes is that we cannot use the DC current here. So it is not possible to use the DC current because we will get accumulation of charges and you will not see any further conduction. So for that reason, the Wheatstone bridge cannot be used. And the second and the most, you can say, the important reason is that it is very difficult to build a bridge like that for electrolytic conductor, which is easier in case of metallic wire. So you simply connect it with the wire and you change the distance accordingly. Then you get the electrolytic conduction of metallic conduction of that metallic conduction or resistance of the given wire. But in case of electrolytic, it is difficult to conduct such an experiment. So we cannot use the Wheatstone bridge to calculate the resistance or conductivity of the given ionic solution. So what do? We use this is called a conductivity cell. So we use this conductivity cell, so it is a standard cell to calculate the conductivity of a given say electrolyte that we have. So how do we do it is that the first thing we did is that we use AC current in place of DC current for this conductivity cell. Okay, so we are using this conductivity cell and we are using this say AC current. Now how do we use it to calculate the thing? So for that, the one thing that is important, that we should be aware about the cell constant of the given conductivity cell. So cell constant is what? It is constant for a, or you can say given for a given for a given like conductivity cell, and it is given by G star is equals to L by A. So you can write it like this, that is equals to R into kappa. So how is it so? So you know the formula that R is equals to rho L by A. Now we have defined a new parameter, that is cell constant. So it is G star, which will be R. Then further G star will be equals to R 1 by rho, and we know that 1 by rho is nothing but conductivity, which is kappa. So this is the same formula that is given here. Now, using this, knowing this value, that is L by A of a given conductivity cell, you put the solution there, then you calculate that conductivity very easily by using that conductivity cell that we have the photo here of this here. So you can use this and this. So two most common are given here. So this one is having a platinum wire. Same one is having platinum wire here also. So this is how the measure of the conductivity takes place. Now the next is the electrolysis. So we will see two application of this electrolytes. First we will see that we are applying current and then we are doing the chemical process. So one of the example is electrolysis, and the second one which we will see is that we are doing a chemical reaction and then we are getting the current from it. So the batteries and the cells we have follows the same principle. So some kind of chemical reaction takes place inside the dry cell, and as the output of this dry means reaction, we get some energy that we use in our daily life. Now first of all we will see what an electrolysis is. So you have studied this thing in class 10th or 9th also. So what do is simply we take a bath. Okay, we take a bath, we fill it with a copper sulfate solution, and further so this is an example of this electro refining. So what we are basically doing is we are taking a copper plate which is having some kind of the impurities, and we are connecting it with another copper that is having pure copper, which is means already refined. And now we are turning on the switch, that is key here. Due to this, now since it is a negative charge, it is positive charge. Now Cu will release two electrons, and it will, after releasing two electron, it will be converted into ion. Now this ion will move toward this negatively charged, can say cathode, negatively charged cathode, yes, cathode, yes. Now it will get stick to it, and what will happen in this process is that only Cu2 plus ion will move, and the unrefined thing, or you can say the impurities, are given in or precipitated in this solution. So this is the example of a electrolysis application, that is electro refining. So many more examples of this electrolysis are electroplating and electrolysis. So what is electroplating? So in electroplating we basically do is what, suppose we have a say iron, and we do not want it to uh, corrode with the reaction of the oxygen. So what do we do is plate it with a certain substance that do not corrode or do not react with oxygen. So we put a thin layer of it. We do the similar reaction. On only the different thing we do is we take this thing here that we have to electroplate with, and the metal or the iron which has to be getting electroplated is put here. Now the same reaction goes on, and the metal slowly and slowly get deposited over this whole iron metal, and we do get a protected iron metal that is not corroded with the reaction with iron. Now what is the thing that is used to govern this electrolysis? So the Faraday has given two laws which is used to quantify this electrolysis. So we'll see those two laws one by one. So the main definition of electrolysis is that it uses an electric current to drive a non-spontaneous reaction. So why are we saying non-spontaneous here? Because suppose we put this circuit and we do not supply any current, we put a closed circuit, okay, but we do not put any battery here or a cell here, and we just put this electrode and we'll leave it for some time, then there will be no reaction because this reaction is non-spontaneous, or you can say the amount of means delta G, that is give free energy, is not negative. For that we apply current, that so that the reaction can take place in non-spontaneous direction or an external factor, you can say. Okay, so this is the thing here. Now what is Faraday's law? So this Faraday's law questions are also asked in the exam sometimes, so you should be aware about it. So the first law says that the mass of the substance that is deposited on the during electrolysis, or you can say any other electrolysis process, is given by Z into I into T, where Z is the electrochemical equivalent. So when we will solve the numericals, we will see what is electrochemical equivalence and all. Into I, that is current, and T, that is the time. So M is equals to Z into I to T. So if you want to know Z, it is nothing but NF into mole factor into molarity, which is N factor into molarity. And the second law says that if we are conducting the same current through two different solutions having different equivalence and different equivalence, then the ratio of the mass that is deposited on each electrode is equals to E1 by E2, that is M1 by M2 is equals to E1 by E2. Okay, so this is the thing here. So this is the Faraday's law of electrolysis. So we will see some examples to clarify what is this law. Now let us move to some questions here. So the first question is from resistance. It says that we are given a solution which is having a 0.2 m resistance. Molar solution is given. So this is the resistance of this thing, and this is the concentration. And the specific conductance is also given, which is 1.3 Simon per meter. If the resistance of the 0.4 solution of this same electrolyte is 260, its molar conductivity is. So we are given two different solutions. The first solution is having a concentration of 0.2 m and a resistance of 50 ohm, and the specific conductance of the solution is 1.3 m, 1.3 Simon per meter. And if the resistance of the 0.4 m of the solution is 260 ohm, what is its molar conductivity? So let us see how this question will solve. So the first thing is we will find the specific conductance of this thing. So we know that specific conductance is given. Then we take the cell constant here. Now it is given that we are taking the same solution. We are taking the same thing. The cell constant will be constant, or it will be same throughout this calculation. So first what we will calculate is the cell constant. So it will be 1.3 into 1 by 50, which is this. So if you solve this, you will get at as 65 by 65 per meter. Now we'll convert it into centimeter inverse, so it will be 65 by 100. Now for the second solution, we have to calculate the molar conductivity. So it will be 100 into 1000 into this. So we know the formula very well. Okay. So it is given as lambda m is equals to kappa into 1000 by molarity. This was the formula. Okay. Now we know that kappa is equals to conductance into G star, which is cell constant. Okay, or you can say 1 by rho is equals to 1 by this thing. Okay, so this use this formula and find the molar conductivity. So we put all this cell, we have calculated cell constant 65 by 100. So this is the final answer. Now the next question we have here, it is that the resistance of 0.2 amp solution of an electrolyte is 50 ohm. The specific conductance of the solution is 0.5 is 1.4. So we are again given two solutions. The first solution is 0.2 m and is having a resistance of 50 ohm, and the specific conductance is 0.5 m. and of the same electrolyte is 1.4 m. Okay, and its resistance is also given. The molar conductivity of the 0.5 m solution of the electrolyte is, so what we have to calculate is that we have to calculate this molar conductivity of the 0.5 m solution. Okay, so I will calculate it. So these are the options we have. Now for the first solution, we know that kappa is given as this and R and M is given. So specific conductance we know it as kappa is equals to 1 by R L by A. Okay. So we put all this and we find this cell constant first of all. Now for second solution, we know that R is equals to this. So we are calculating this kappa here. We know the cell constant. Now we have to calculate the molar conductivity, which is kappa into 1 by 1000 into m. So why are we using 1000 here? Because we have the meter thing here, so we will convert it into centimeter. That's why we use this. Okay, because we have find it in meter. Okay, so do not get confused. So why it is written 1000? So this is the final answer. Okay, 5 into 10 to the power minus 4. Now the next question is, we have to find the equivalence conductance of NaCl at concentration at infinite dilution lambda c, lambda infinity respectively. So this is nothing but the Debye-Huckel-Onsager equation. You have to find which one is the correct one. So we know very well it is this one, which is lambda c is equals to at given concentration is equals to at infinite dilution minus b root c. So same thing is written here, where lambda c is the limiting molar conductivity at concentration c and the liquid at infinite dilution. Okay. The next question we have here is that the equivalent conductance of two strong electrolytes at infinite dilution in H2O at 25 degrees Celsius is given as this and this. Okay. So what additional information one needs to calculate lambda naught m of aqueous solution of acetic acid? So this question is mainly from the Kohlraasch law. So it is given that lambda is equals to CH3CON. Okay, for given it is for this solution and for this solution it is given, and we have to find it for the acetic acid. Now the question is asking that what extra information should we have so that we can calculate it for the acetic acid. Why? Because for acetic acid we cannot calculate simply by using this and this, because if you want to calculate, let us see what happens. So we know from Kohlraasch law very well that CH3COOH is equals to lambda of CH3COO minus plus lambda of H plus. Also, so it is of Na, na? So it's Na is given. So it will be Na plus. And for HCl it is given as lambda of H plus plus lambda of Cl minus. And what do we need? What do we need to find is that, let me write with a different pencil. So we need to find it for CH3 COO H. So it will be CH3 COO minus plus CH3 H plus. Okay. So we have this. But if we add this both of this, suppose we add both of this. So what we will get is that lambda of CH3 COO minus plus lambda of H plus lambda of Cl minus plus lambda of Na plus. Now we need this one and this one, but we do not need this one and this one. So we need to subtract this Na plus and Cl minus from this. So if we have the molar conductivity of NaCl, so we can subtract it from these two equations. So finally we can write that. So we can write finally that lambda of CH3COH is equals to lambda of CH3 COONA plus lambda of HCl whole minus lambda of NaCl. So if we have this NaCl, then we can calculate this answer. So this one is the correct answer here. Okay. So solution says the same. So according to Kohlraas law, for determining the molar conductivity of CH3COH solution, we need this NaCl. Okay. Now let us see our last question that I will solve. Now from the next question, you will solve all those. So I just give you a hint about all of those questions one by one, and then you will solve this question by your own. So it says that 2 Faraday of current of electricity is passed through a solution of CuSO4. What is the mass of the copper deposited at the cathode? So we have to calculate the mass. We know the formula. So mass is equals to Z into I into T. So it is the Faraday's first law. So let us see how we will solve it. So we know that the amount of charge that is flows through is given as Q is equals to 2F, and the atomic mass is 63.5, and the valency, or the you can say n factor, is 2. So we will do it like this, which is 63.5 by 2. It is into 2. So you can see here that equivalence is given as molarity into 2. Okay, this is the thing here. Sorry, Z is equals to E by F. Okay, so what we are doing basically here is that we are dividing this n factor, which is 2 here, by the molar mass of this, or the molar mass of this Cu, and then we are using the formula that is Z is equals to I into T. So we are replacing here I into T by Q, so do not get confused with it, because current is nothing but charge flown per unit time. So if you find out Q, it will be Q is equals to I by T. So using this, you can find the mass deposited, which will be equals to 63.5. Okay, so this is the correct answer. So yeah, this will be the answer. Now let us move to next question. So solution will not be given. I will just give you a hint of it, and you have to solve it by yourself. So three informations are given, that is lambda equivalent of NaCl, lambda of KCl, and lambda of K2SO4, that is 123.5 0.7, 140 147.0, and 152.1. And what we have to find, we have to find it for Na2SO4. Okay, so we know two things, that is lambda of Na plus and lambda of SO4 2 minus. So if we have these two, we can calculate our required answer. First of all, if we see these two equations, see, so you have to just split this equation individually. You can write it as lambda of Na plus lambda of Cl. Here also lambda of KCl, K, and lambda of Cl. Similarly, lambda of 2 into lambda of K plus lambda of SO4 2 minus. Okay, so this is the thing we have here. Now first of all, we need it for Na. Okay, but we do not need K, so we will multiply this by 2. Okay, and also this by 2. So it will give us this thing and this thing. Now if you subtract it, if you add this to this thing, and say I can do it for you if you want, so it will be Na plus and Cl and Cl minus. Okay, then we have, I'm multiplying it by 2, do not get confused with it. It will be Cl minus. Similarly, it is of 2K plus and SO4 2 minus. Okay, so this is the thing. So if we add this 2, okay, and subtract this one, so what it will give, so it will give 2 lambda Na plus, of course, then This one and this will get cancelled. Okay. Similarly, this and this will get cancelled, and we will get SO4 2 minus. So you must have gotten an idea. So you have to multiply the lambda infinity of this by 2, this by 2, and add this the resultant of this 2 and subtract it from KCL, then you will get your required answer. Now the next question says that you have, I will not solve this because theoretical question, you have to do it by yourself. I'm just making the statements clear. So among the following statement related to ionic conductance, choose the correct statements. The ionic conductance depend upon nature of electrolyte. An ionic conductance due to the movement of electron. Ionic conductance is called electronic conductance. Ionic conductance depends on temperature, and ionic conductance also depends on the nature of solvent. So to solve this question, the one thing that should be kept in your mind, that what is conductance first, and what is ionic conductance, and what is the difference between both of this, and does ionic conductance is an extensive property or an intensive property. Ionic conductance is not a different thing, it is similar as conductance. Not get confused that why treating ionic. So if, say we are referring it to this electrolyte, it has just specified that okay, we are calculating it for a electrolytic solution, so we are writing here ionic conductance, so it is similar as conductance. Now you can solve the question by your own. Now the next numerical we have here is the specific conductance of a solution is this. Okay, specific conductance is given, that is resistivity, or you can say kappa, or you can say kappa. Okay, so kappa is given 0.176 Simon sorry, omega inverse centimeter inverse. Cell constant is given, that is G star, that is 0.255. You have to find the conductance, so it is very easy. You just know the formula. You have to know the formula very well. It is R is equals to rho L by A, or you can write 1 by rho is equals to, that is kappa is equals to G into G star. Okay, so use this formula, you will get your answer. Now, this is also a theoretical question, so I will now solve it for you. So, Debye-Huckel-on-Segar equation is for salt, weak electrolyte, weak base, or electrolyte. So, you can solve it by yourself. Now, the next one is conductivity is equals to what? So, conductivity, what is conductivity? It is kappa, or you can say 1 by rho, 1 by R, L by A. So, this is the correct formula. So, this one is also a correct formula. Why? Because L by A is nothing but G star. So, it will be 1 by R is equals to lambda m. Okay, so lambda m is not equals to kappa, because lambda m is kappa into 1000 by molarity. Next is 1 by lambda, but is also wrong. Okay, so this was for today's class. So if you have any confusion, you can ask questions. So in the next class, we will be mainly seeing the Nernst equation first of all, and we will see how we have the thermodynamic aspect of it, that is Gibbs equation now. So the next class is more important because mostly the questions are asked from the electrochemical series, but the first part contains some easy part. So if you know the simply the formulas, you can calculate the equations, and you can get your answers. Okay, so do not miss it.